So we next see convergence in a discrete metric space. So let's see what the statement of this proposition says. Here we have a set X and we have the discrete metric D disc on X. So X is a discrete metric space. And we have this sequence X then in X, and there is also a point X in X. Then the sequence converges to this point with respect to the discrete metric if and only if there exists an integer n, capital N, greater than or equal to the minimum value of this index n, that is m, such that the terms xn of the sequence are all equal to that point x for all n greater than or equal to n. There is another way of expressing this thing. When this happens, we say that the sequence xn is eventually constant. That means starting from some stage, all the terms of the sequence are equal. When that happens and only when that happens is such a sequence convergent in a discrete metric space. And we are going to see the proof in this exercise 13. So let's see what comes next. Next we have this proposition, uniqueness of limits. It's a fact that we have already seen for sequences of real numbers, that when such a sequence converges to a real number, that real number is unique. That same thing is true for convergence of sequences in a general metric space. So the statement just simply goes like this. This is the metric space where D is the metric, and this is the sequence in X, and let X and X prime be 2 points in X, such that this sequence converges to both X as well as X prime with respect to the metric D. Then X has to be equal to X prime. And the proof of this fact we will see in exercise 14. Now this fact lets us create a notation for the limit of a sequence in a metric space. That's the next thing. So this is the thing. Because of the above proposition, each sequence in a metric space either has a unique limit or it does not have any limit. So we can create some kind of notation for the limit, and that notation is just this. If xn is a sequence in some metric space converging to a point x in that metric space with respect to the metric D, then we express that by writing this. So this part of the notation is our usual limit, where you have the limit symbol n approaches infinity, the term, general term xn, and on this side you have limit. But to emphasize the fact that the convergence is with respect to the metric, we write D dash. And we can actually not write D also and write more simply like this, like how we write sequences and their limits, sequences of real numbers and their limits. The usual notation, if it is understood what the underlying metric D is. If you are working with say 2 or 3 metrics, then you should write D. Otherwise, if you are working with only one metric and you know that in your discussion that is the only metric, then you can write this more simple notation. Alright. Now next let us see one example. In that example, we will see what happens if we change the metric. We have already seen in the previous examples while working with Euclidean metric, taxicab metric, but another such example. Let's see. Okay, so that example is contained in this remark. The remark starts by considering this ordinary closed interval in the set of real numbers. So you know that this is a subspace of R, so that we have the ordinary metric D on R also on this, restricted to this. And in this metric space we have the sequence of reciprocals of positive integers 1 divided by n. And we also know that this sequence converges to 0. In fact, this is the first limit ever that we proved in single variable real analysis. Okay, now if we change things a little bit, say we swap the positions of 0 and 1. This may sound a little confusing because actually we are not changing the set X, but the details will become clear. Let's see what it is. So what we are doing is we are defining a function from x into itself, that is from this closed interval into itself, like that. X interchanges 0, f interchanges 0 and 1. F of 0 is 1 and f of 1 is 0, and it does not change anything else. If you take x from this interior of that interval, then f of x is just x. Now with the help of this function f and the original metric d, we are going to define a new metric d prime on the same set x, like this. So the distance between x and y in the new metric is the distance between f of x and f of y in the old metric. The fact that this new metric really is a metric is left to you to prove. In fact, you will see that this is almost evident. Let me just go through a few of the axioms. What do you need to prove that this is a metric? Always keep in mind that whenever you define a new function in any place, you have to see that the function makes sense and it's well defined. So what type of function are we talking about? It's a function whose domain is the Cartesian product x times x. So obviously the input of the function will be an ordered pair of elements of x. So x and y are both coming from x. For them, this d prime is defined to be equal to this. For x and y coming from x, where is f of x and where are f of x and f of y lying? Again in x, because f maps x into x. So fx and fy are again points of x, and their distance can be calculated using the old metric d. What is this right hand side? This right hand side is a non-negative real number because d is a metric. So yes, for any two points from x, their d prime distance is a unique non-negative real number. So that means d is a well-defined function. Now you can work with d. What is the next thing you have to show? Say you take two distinct points x and y. You have to prove that their d prime distance is a positive real number. You already know that it's non-negative, but it should not be 0. If x and y are distinct, are fx and fy also distinct? Yes, because this function f is a one-to-one function. That you have to convince yourself that it is a one-to-one function. Or you have to actually show. That also is very easy. So fx and fy are also distinct, and since the original d is a metric, so this d distance will be positive, and that way this is also positive. Next, let us take x to be equal to y. We have to prove that the d prime distance is equal to 0. If x is equal to y, then fx and fy are also equal because f is a well-defined function and d is already a metric, so that is why this will be 0. So yes, we are also getting 0. What about symmetry? D prime of x comma y is this. D prime of y comma x will be d of f of y comma f of x, but that is equal to this because d is symmetry. That is why automatically d prime is also symmetry. Similarly, you will have triangle inequality, about which I won't say anything. So you get convinced of this fact that d prime really is a metric. Now with respect to d prime, however, that same sequence converges to 1, not 0. You see why this is the case. Okay, I am not going to say how, because this is something you should be able to get at this stage. So you see that if we change the metric, then the nature of convergence also changes. That same sequence will converge to something else. It all depends on how we define distance or how we measure distance in a given space, which the author says is topology, in a sense, this nature of convergence. See, if you are simply thinking of mathematics, these things may seem like some artificial constructs that we just forcefully swapped the places of 0 and 1 in some sense and made the limit here 1 in place of 0. But things really change in physics also. Most of us already know that when you have an extremely heavy object somewhere, it bends the space-time around it because of its gravity. The details are of course very complicated. I also don't know, I want to know. So in that bent space-time, your ordinary Euclidean metric is no longer applicable. There you have to apply some other metric. It's like that. Okay, so these are not just some mathematical games. When used in applications, they really give you the answer that you should get or you are trying to get. So with that, anyway, this section ends, and next week we will start solving exercises. And tomorrow I think we again have differential equations, because last week we did number theory. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.